In the last video, we asked if every absolute value on a number field K comes from some kind of discrete valuation. Well, let's see. How about we consider the usual absolute value on Q? Does this one comes from some discrete valuation? i.e., does there exist some valuation V from Q star to Z and some positive constant C less than 1 such that the absolute value of every rational number A is just gonna be equal to C to the VA? Well, if there does indeed exist such a valuation and such a constant, then we should have that the absolute value of the sum of two rational numbers A plus B should be equal to C to the valuation of A plus B. Now recall that the valuation of A plus B is always greater than or equal to the minimum of the valuation of A versus the valuation of B. For example, in the three-adic valuation case, we see here that 9 plus 6 is 15, so V3 of that is equal to 1. Whereas V3 of 9 is 2 and V3 of 6 is 1. So indeed, V3 of 9 plus 6 is greater than or equal to the smaller one between these valuations. This is really just due to the distributive property of multiplication over addition. Now coming back, since C is between 0 and 1, this inequality implies that this absolute value of A plus B must be less than or equal to C to the minimum between VA and VB. Now since C is less than 1 greater than 0, smaller exponent here means bigger result. So we see that the absolute value of A plus B must be less than or equal to the maximum of these two absolute values. In other words, this absolute value has to be non-Archimedean. Thus we see that if an absolute value is induced by some discrete valuation, then it must be non-Archimedean. So, is our usual absolute value on Q non-Archimedean? Well, obviously not, since if it is Archimedean, then if we take any natural number m, we can write m as a sum of ones. Right? So by this non-Archimedean property, the absolute value of any natural number must be less than or equal to 1, which is ridiculous. Actually, this is where the name non-Archimedean comes from. You have probably heard of the Archimedean property in real analysis. It basically says that the natural numbers are unbounded. As we saw, when this strong triangle inequality holds, then every natural number is bounded by 1, i.e. the Archimedean property fails, and thus we call this a non-Archimedean absolute value. Thus we saw that every discrete valuation V induces a non-Archimedean absolute value. This gives a necessary condition for an absolute value to be induced by a discrete valuation, namely, it must be non-Archimedean. Now we can ask if this is also a sufficient condition. In other words, does every non-Archimedean absolute value come from a discrete valuation? Well, not really. However, if we drop the condition that the valuation is discrete, then we do indeed have a bijective correspondence. That is, every non-Archimedean absolute value comes from some valuation. Now, a general valuation has the same definition as a discrete valuation, except that we drop the condition that the value groups have to lie in Z. So, how do we recover a valuation from a non-Archimedean absolute value? Well, to do so, we just need to reverse the process of obtaining an absolute value from a valuation. Recall that given a valuation V, we can obtain an absolute value by picking some number C between 0 and 1, and then define the absolute value of every element A in the field to be C to the VA. This gives us an idea of how to reconstruct V from the absolute value. Now, given an absolute value on K, we can again just pick some constant C and then define a valuation by VA is equal to log C of absolute value of A. it's not hard to check that this is actually a valuation. Thus, we have some kind of correspondence between non-Archimedean absolute values and valuations. We want to say that this is a bijection, but to do so, first we want to define what it means for two absolute values to be the same or two valuations to be the same. In other words, we want to define some kind of equivalence relations on these sets, and that's what we'll do in the next episode.